Hello everyone. We are starting a free open lecture in our Discord. All our lectures are held weekly without breaks. If you, the viewer, want to ask questions and get answers in an online format, join our lectures. You can find the link to Discord in our Telegram channel. To find out the schedule for the lectures, join our Telegram channel. This was indeed a regular heap. Now we move on to the binomial heap. What is a binomial heap? We will be using a binomial tree here, not a binary tree. What is the essence of a binomial tree? How is it formed? Here, each tree has a rank. The lowest rank is 0, and then it goes to 1, 2, 3, and so on. What does a rank 0 tree look like? Here, if anything, I will write the rank of the tree in the nodes, not the elements that are in it. And this is just one node in which something is stored. This is a rank 0 tree. Now, what does a rank 1 tree look like? A node is connected to another node. This is a rank 1 tree. What does a rank 2 tree look like? Well, let's draw a rank 3 tree as well. How will it look? A rank 3 tree. Now I understand how phenomenal trees are constructed. Our most basic point is the rank 0 tree, which is simply one node. How to create a tree? That is, we have a tree of rank k, and we want to create a tree of rank k plus 1. How can this be implemented? We take a tree of rank k. In this case, we want to go from 0 to 1. What do? We draw a tree of rank 0 here. So this is a rank 0 tree with one element. If we then attach another rank 0 tree to it, as a result, we get a rank 1 tree. In analogy, how do we make a rank 2 tree? I draw a rank 1 tree. Here it is, identical. And I take another rank 1 tree and attach it. 1, 2. Here I have one rank 1 tree, two rank 1 trees, and then all of this tree is a rank 2 tree. How do we make a rank 3 tree? Similarly. So we take a rank 2 tree. I will just copy it. And I will take another rank 2 tree and tie it to it. Like this, I end up with a rank 3 tree. The first tree is rank 2, the second tree is rank 2, and together they make a rank 3. Now how do we create a rank 4 tree? Well, by analogy, we just take and copy a rank 3 tree, and then we attach another tree to it. This gives us a rank 4 tree. So what can we notice here? So, for a tree of rank k, we have k children. For example, at rank 0, the root has no children, so it has 0 children. Here is a tree of rank 1, where the root has 1 child. A tree of rank 2, 2 children of the root, 3 children of the root, 4 children of the root, and so on. How many elements are in such a tree? If we draw it, how many elements are there? Or how many nodes are in a tree of rank k? There are 2 to the power of k children, since 1 and 2. So, there will be 2 to the power of k children. That's it. This is auxiliary information for us. Why? To understand how the binomial. So far, these have been binomial trees.
Want to become a great programmer? Subscribe to our Telegram channel.
Now we can move on to the binomial heap. Let's immediately define what operations can be performed on it and what the complexities of these operations will be. Operations. Well, the same goes for get min, push, and extract min. The same 3 operations. And also, 2 more operations appear here. The first is merge. We take some other heap and merge the 2 into 1. And there is also the operation decrease key, which takes a certain value and replaces it with a new value. This is a binomial heap, and these are the operations it allows. As for decrease key, when we discuss it, I will explain what it is. Well, these are also the same. Merge is simply the combination of 2 heaps, meaning we have 2 sets, and we take these 2 sets and merge them into one large set. So what will be the complexity of the operation? Well, actually, here we have also 1, and all these operations will be performed in logarithm base 2 of n. So, what makes this heap better, so to speak, than a regular binary heap? Well, it seems that for these operations, it's the same 1 and e logarithm, these 2 operations. Now let's think about the binomial way, how we can perform the merge. Well, here, if we base it on the properties of the tree, it's unlikely that we can perform the merge quickly, so I will write it here in the regular heap, and the merge with the other heap is performed. how much? We have two heaps. One is a bit larger, the other is smaller. And to merge them into a new heap, what do? Let's say we have size n here and size n here. We simply go through this heap. But how do we go through it? We remove the minimum elements from the small heap. Therefore, we will need to perform the removal operation m times. How long will it take? It will take logarithm time. 2 here with m, this is from this heap, we remove the minimums and take them accordingly. We will add these minimums to the larger heap. How many times will we add them? M times, and the addition will be performed in logarithm n. Accordingly, we can factor out m here. We will get the logarithm of m plus the logarithm of n, and when we add the logarithms, we can actually combine them into a single logarithm. We will have log m multiplied by n, where m is respectively less than n, and then the complexity of merging two heaps will have this complexity, m log n. Well, that's already significantly worse than the log here. Well, the decrease key is basically just about raising it, so the decrease key or some new key will also be executed with a logarithmic complexity. You just need to go through it like that. So a binomial heap is essentially an optimization of a regular binary heap, and it optimizes exactly one operation, the merging operation. If we do not need to perform this operation, then we can comfortably use a binary heap, which is generally implemented in any standard library. You will have to implement binomial heaps and Fibonacci heaps. However, explaining Fibonacci heaps is worth it. For binomial heaps, use Fibonacci heaps.
Want to become a great programmer? Subscribe to our Telegram channel.